What's up, y'all? It's your boy, Big Perv, back again with another video. This time, you sub is what we're going to be talking about. So, first of all, I want to talk about your reading habits. Have you ever read one of these books? Not one of these like particular books, but like the Choose Your Own Adventure series. Dude, I hated this series because I hated choosing which way my character was going to go. Like, you always ended up with this, like, if you want to go to the roof, turn to page 37. If you'd rather go to the basement, go to page 92. And no matter what I picked, my character always died. I hated it. I wanted the author to tell me what my character was going to do. I didn't want to pick. I didn't like that. Integration techniques, this unit is going to feel a lot like that Choose Your Own Adventure book series. Sometimes the pattern is going to change. If you want to use the sign pattern, go to this page. If you want to use substitution, go to this page. If you want to do integration by parts, go to this other page. If you'd rather curl into a little ball and go onto Wolfram Alpha and look up the answer, then don't read the book at all. Just do that. We have lots of choices with integration patterns. Just like the derivative rules, we had some choices. Sometimes we use product rules. Sometimes we use the chain rule. Sometimes we used scratch that last one. Sometimes we use the quotient rule. Sometimes we use trigs. We get choices, right? The choice in mathematics sometimes is the hardest choice to make because you don't always know if that choice is going to lead to something good or the death of your character or the problem that you're working on. There's always a mathematically righteous pathway to take, but there's also a path that leads nowhere, and you got to go back and start from the beginning again. All right, but first, remember derivatives? Yeah, the only derivative rule that always was applied was the chain rule, right? No matter what derivative, no matter what function I was taking the derivative of, I always had to use the chain rule, right? So that was always happening. I always had to take the derivative with respect to a certain variable. The derivative of x squared would be you wouldn't say that, right? We do, and we know what we mean, but mathematically, pure way to say that would be the derivative of x squared with respect to x, right? So the derivative of x squared with respect to x would just be 2x. The derivative of sine t, we know what we mean, but purely, we would have to say the derivative of sine t with respect to t. Well, that's just the cosine of t. And then the derivative of e to the q with respect to q. That's just e to the q. Now, when those letters were different, okay, that's when things got a little bit funky, right? And we don't feel the chain rule here, but indeed, the chain rule is being applied. Technically, the derivative of x squared is 2x, but we need to multiply by the derivative of x with respect to x, right? And that was just 1. The derivative of sine t is cosine t, but we have to multiply the derivative of the inside critter t with respect to t. So we'd have this dt, and then this last one, we'd say dq with respect to q. And that always turned out to be 1. But a different way to write it, other than dx dx or dt dt or dq dq, would just be to write it as dx dt or dq. This representation of the derivative of x, the derivative of t, the derivative of q. And what you might notice there is that is the notation that we see with integrals, right? That's why the integral has that little differential piece at the end. Not only does it signify that a definite integral is a product of a function times a width, right? Height times width, that's a rectangle that gives us a product, a definite integral. We talked all about that. But it also shows us the manifestation of the chain rule. So the integral of sine x dx tells us that x is this inside critter, and we've had to multiply by the derivative of it, right? You see these other examples that dx is the manifestation of the chain rule. So could you just integrate x squared? Could you do that? No, you can't. Why? Because the chain rule hasn't happened. There is no derivative out there in the universe where the chain rule has not been applied. You can't integrate x squared. I know you wanted to say x cubed over 3, but pump the brakes there, champ. You got to take the integral of x squared with respect to x. You got to have the chain rule before you can reverse the derivative. All right, hopefully that makes sense. If it doesn't, you always can watch it again or go somewhere else or ask a friend. Choose your own adventure. Okay, so here we have 3 integrals where we see an easy pattern, right? So that dx is the manifestation of the chain rule. We've kind of established that. But when we're trying to find an antiderivative, sometimes it's like easy, right? X to the 7/3 dx follows this anti-power rule. That'd be simple, right? We just do x to the, we're going to add 7/3. We're going to add 1 to that. So that would be 10/3. And then multiply by the old reciprocal of that. So 3/10. And then add this mystery constant. The next one, 3 over 4 plus t squared. If I think hard enough, I can figure out what that pattern is. It fits the arctan pattern. This is why the patterns are so important, because you need to be able to recognize the pattern of integration. So I could factor the 3 out. All right, see you 3, you're gone. So then we got 2 squared there, right? So this totally fits arctan. This would be 3 times 1/2 times the arctan of t over 2, and then add that mystery constant of integration. And this next one, we got a piece by piece integration, 3 to the a, dA. Well, a is the variable of choice here. There's nothing special about that variable. It's just a dA. That's what we're taking the integral with respect to. So that would be itself 3 to the a divided by the log of 3. And then secant squared a. Guys, if you don't know your trig derivatives, I can't help you. Morris can't help you. Wolfram can't help you. You got to know your rules. Antiderivative of secant squared is tangent, and then of a plus the mystery constant. Those just fit the patterns easily. Now, there are other integrals out there. There's other functions out there that we want to integrate that are not easily fitted to a pattern. Like these. These look totally rambunctious, don't they? Look at the, hey, I'm getting anxious just thinking about these daggone things. Now, secretly, all 3 of these do fit an integration pattern. But what is required is this idea of substitution, right? Some substitutionary expression to make each of these crazy looking things fit one of the integration patterns. So we're going to have to do a U substitution. U is just the letter of choice. There's nothing special about U. It's just the letter we use in calculus. I don't know why somebody had a big hankering for U, but we're doing it. And that U is chosen by us. See, you hear that choice. So what that means is, sometimes you're going to pick the right U to make things work out. Sometimes you're going to pick the wrong U. You're going to hit a dead end in your story. That means you got to go back to where you started, try something different, make a different decision. You don't always pick the right thing the first time, especially when you're new to this. So I encourage you to keep going. Don't worry if you hit the wrong road. Even doing things wrong is informative. Don't let it just totally dead end you. Okay? Know to go back and start again. Let's talk about how we're going to use U substitution. All right, let's get to the meat here. Now, 2x minus 3, the quantity to the 7/3. right? There's nothing I can do there. I can't algebraically simplify. I can't expand. Like if it was 2x minus 3 squared, maybe I could expand and go with it. But raised to the 7/3, I got no recourse here algebraically. So what I want to do is I want to make a substitution. I want to make this thing simpler by looking for u as a function within a function. That's what happened with chain rule, right? We look for a function within a function, that composition idea. So let's set u equal to that inside function, 2x minus 3. Now what I want to do is I want to set up a u filter. And by that I mean that the expression in terms of x is going to go through this u filter, and then on the other side, it's going to come out all in terms of u. That's something you all did on that little introductory worksheet, the y-o-u substitute, right? So here's what we got to do. Our u filter is going to be set up as u is 2x plus 3 or minus 3, but what we've got to do is take the derivative. We've got to understand that if I was taking the derivative of this antiderivative function, I would have had to multiply by the derivative of that inside critter. So we need to figure out what du dx is. What is the derivative of u with respect to x? Well, is just 2. So one thing that I can do to simplify things a little bit is just multiply both sides by dx. So I have an easy way to swap out a dx for a du. Now let's talk about how we're going to do that. So here is the u filter. We want to chuck that integral into the u filter and have it pop out on the other side, all in terms of u. So let's look at that. That's going to be the integral. Well, I think it's going to be u to the 7/3, but maybe not so is what happens with the dx. Now, I certainly can't just write the integral of u to the 7/3 dx. There is no such thing, hallelujah, as implicit antidifferentiation. Whew, dodged a bullet there. So you can't write u to the 7/3 dx. That's multivariable calculus. We're not there yet. So we don't want to put u and dx. That's a mixture. We don't want to go there. So how do we manufacture the 2dx that is required to swap out for a du? Well, we're just a multiplier away. So very quickly, multipliers are pretty cheap, right? I can multiply by a number, like I can multiply by 2, but if I multiply by 2, in the original problem, I have doubled the function, and that's not what I want. So I also need to remember that to multiply by the reciprocal, thus multiplying the function by 1 and keeping everything the same. So I'm going to multiply by 2 to manufacture the 2dx, but I'm also going to multiply by 1/2, and I can do so on the outside because constants can be pulled in and out of the integral. We know that. So let's see what we've got. The 1/2 that's outside is going to come along for the ride, but this 2dx, into the u filter it goes. 2dx is going to get swapped out for a du. And I hope you saw that action, because now we have an integral in terms of u that fits the power rule pattern. That's going to be easy from here, right? We got 1/2 u to the 10/3 multiplied by 3/10. Add the constant of integration, simplify what you need to simplify. So we'll say 3/20, but we don't want to write it in terms of u. We can just simply swap back in what that u was, and the u was 2x minus 3. Now the fail-safe method for seeing whether you did that right is to not only check the answers that we will provide, but also take the derivative of your answer. Right? If you take the derivative of your answer and get the original problem, you did it. If you don't get it, well, then something happened on your path. You might want to go back and make a different choice. So let me show you a couple more examples and then I'll be done. I know I'm getting long-winded, but I hopefully you're enjoying it so far. You're seeing how things are working. We're just trying to build the idea of u substitution. So this next one, let's take a look at it. Ooh, wait, That totally looks like arc sine, doesn't it? That totally looks like arc sine. That square root of 4 minus x squared in the denominator. Okay, if we just factor out the 3x, yeah, we're good to go, right? We're good to go. Fits the arc sine pattern, but
uh-oh, can I do that? I can't do that.
Why can't I do that? Oh, y'all are screaming at me. I can hear it. I can hear it digitally here, and even in this video that I'm making. You can't factor out x's from definite integrals. You can only factor out constants. The 3 could come out, but certainly not the x. That means this doesn't fit the arc sine pattern. So we need to somehow come up with some substitution that's going to make this thing easier. How about if we make u equal to that thing that's inside the square root? What if we say u is 4 minus x squared? Let's see what happens if I do that. Well, if I do that, I can say that the derivative of u with respect to x is negative 2x. Thus, du is negative 2x multiplied by dx. So here's the u filter. I know how to get u. I know how to get du. I want to send that sucker through and see it come out on the other side, all in terms of u. Now, the easiest thing to see would be that the denominator is now the square root of u. That's pretty easy to see, right? But let's look at the rest of it. Okay, we need negative 2x dx, and what we got is 3x dx. We're a constant away, and constants come cheap. So let's do a couple things. Okay, one thing I can do is factor out that 3. Now I need a negative 2. Well, I can simply multiply by negative 2 to get it, but that comes at a cost. I got to divide by negative 2 or multiply by negative 1/2. Now everything is all hunky-dory. I got the negative 2x dx. That, ching, 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 is du. And then that negative 3/2 comes along for the ride. Well, what do I have now? Oh, wait, I see it, don't you? That is just u to the negative 1/2 du. Dude, that is power rule all day. Let's do it. Negative 3/2 u to the positive 1/2, multiply by 2, add our constant, and then we want to rewrite that in terms of x by subbing back in the u. So that'll be negative 3 times the square root of 4 minus x squared plus the mystery constant. So there would be my antiderivative. Now, I'm going to cut it here. I've got a couple more examples on this document, and I don't want to make this video super long. So I'm going to cut it. In the next video, I'm going to talk about a few more tougher examples of when u substitution is going to come in handy, how things might look a little bit tougher, and those are the fun ones. But I want to just reiterate, why did I choose what I chose for you? You might be asking that question. Why did you choose 2x minus 3? And why did you choose 4 minus x squared? So I just want to highlight something for you guys real quick. U is normally going to be the function within the function. It's that piece that's inside of some other function. Or the u could be, if the derivative of one thing is somewhere else in the integrand, you can also do u substitution because that derivative part is going to get gobbled up by the du. I hope you guys got a chance to follow me through this craziness with the choose your own adventure stuff. I want to really encourage you to keep trying. Like I said, u substitution is not for the faint of heart. You're going to get to places where you're not sure what to do. Forge ahead. Keep going. If you need to go back and try again, do it. This is going to take work. Please join us in this adventure. Thanks. See you guys next video.